Hello everyone, I welcome you all to Physics Wala, and in this session we are going to start the new portion of our organic chemistry, which is nothing but a very interesting and indeed a very important chapter, that is hydrocarbons. And this is the lecture number 1 of hydrocarbon. So let me tell you what we are going to discuss in this particular session. First of all, we are going to revise all the concepts whatever we have discussed in case of GOC, like the introduction part of hydrocarbon. Next part will be the nomenclature. Next part will be related to the isomerism part, and last part will be the preparation method. If time permits, definitely we are going to complete the preparation method. Now, before starting, if I talk about the simple introduction part of hydrocarbons, I can simply say the term itself says that we have hydrocarbons. What is the meaning here? What is the meaning of hydrocarbon? It's very easy. We are talking about the all compounds, all covalently bonded compounds of carbon and hydrogen. So first of all, we are going to deal with the compounds of carbon and hydrogen only. But is this chapter only related to these hydrocarbons, or we have other portions? So basically in organic chemistry, first portion always starts with simple compounds which are covalently bonded between carbon and hydrogen. Now rest of the part is basically derivatives of hydrocarbon. So this entire part, which is basically the derivatives of hydrocarbon, in that case you can see that we have first part which is known as haloalkanes and haloarenes. Means in that case one hydrogen is basically replaced by a halogen group. It must be chlorine or bromine or iodine or fluorine. That part is basically the derivatives of hydrocarbon. Then you are going to deal with alcohol, phenol and ether. Basically the compounds containing oxygen as a functional group. Next part will be carbonyl compounds. So basically all those compounds in which C double bond O group is actually present. Basically this deals with the compounds of aldehyde as well as ketone. Then we have the next portion which is carboxylic acid and derivatives. So basically all those compounds in which COOH moiety is actually present. And last part will be nitrogen containing compounds. So first of all, if I talk about this 11th class only, in 11th class we generally deals with simple hydrocarbons, and rest of the part you can find in your 12th class. These are the chapters, main chapters of organic chemistry, in which any of the hydrogen is replaced by or substituted by different type of side atoms, you can say. Either we have FCl, or we have OH group, or we have the next part which belongs to C double bond O group or COOH group, as well as its derivative like acid halide, like amide, all those type of structures. And last part will be nitrogen containing compounds, which are mainly amines, you can say, as well as amides. So this is the entire portion, basic portion of organic chemistry. But in 11th class only, we have only hydrocarbons. And if I talk about the description of these hydrocarbons, so basically in these hydrocarbons we are going to deal with 3 different type of compounds. First one is carbon single bond carbon, next one will be carbon double bond carbon, and last one will be carbon triple bond carbon. So basically this chapter has 3 portions. First one is simple alkanes, next part will be alkenes, and last part will be alkynes. So what type of things we are going to study in this particular chapter? So always remember, the entire analysis of organic chemistry always starts with the introduction part, which comprises of nomenclature, structure analysis, as well as isomerism part. Okay, if I talk about the next part, which is the preparation method, preparation methods. Okay, preparation methods for simple alkanes, alkenes, as well as alkynes. Also, we are going to include one more category, which is a subtopic of alkanes known as cycloalkanes. That part also we are going to discuss in the preparation method. What type of preparation methods we are talking about here? Very easy, very easy, very easy, very easy. In that case, we have lab method, laboratory method, we have manufacturing process, along with that we have some important name reactions. Okay, and last part, if I talk about the last part in this particular scenario, if I talk about the last part in this scenario, then we are talking about the physical and I can say chemical properties of hydrocarbons. It means we are talking about the different type of reactions. That's it. That's it. So this is the flow of the entire part which corresponds to your hydrocarbons. I hope this part is clear. I hope this entire part is clear. Okay. Now, if I talk about the first part, definitely we are going to start with the nomenclature part. We are going to start with the nomenclature part. You already know how to write down the names of these compounds because we have already discussed that entire part in the nomenclature. If you haven't watched that entire part of the nomenclature, or if you don't know anything about the nomenclature, you can refer to the lectures of nomenclature of organic compounds, which we have already been published in the YouTube channel. You can watch that entire part. Okay. But if I talk about the basic analysis, I'm going to start with the entire analysis part. So first of all, if I talk about the nomenclature, the basic idea is you have to find out the word root that corresponds to maximum number of carbon atoms in parent chain. In parent chain. So first of all, you have to find out maximum number of carbon atoms. It must be 1. If it is one number of carbon atom, it is meth. If 2 eth, 3 prop, 4 but, 5 pent, 6 hex, then sept, and then hept, and it's going to be oct, non, then dec, just like that. Then you are going to use primary suffix, because we are talking about only hydrocarbons, so that part is relevant. If we have a single bond, then it's supposed to be ane. If a double bond, it is supposed to be ene. If we have a triple bond, it is supposed to be ine. Okay. If we have other functional groups also, then we can use secondary suffix. Which talks about the presence of functional group. But we are talking about only simple hydrocarbons, so we are not going to include that particular part. Now we also have primary prefix. Here we also have primary prefix. So in case of primary prefix, it is generally used to denote the cyclic structure. Cyclic structure. It should be bicyclo. It's going to be simple cyclo, or it's going to be spiro. These type of primary prefix are generally used, and last part will be your secondary prefix, which generally talks about the presence of your side substituents. I hope this entire part is clear. So in case of hydrocarbons, which things are more relevant? Definitely, you can say, definitely in the entire process that secondary suffix are important, secondary prefix are important, primary prefix are important, definitely word root is important, and last part is primary suffix is important. If you know these things, then entire part will be clear. I hope this part is clear. In case of C1, we can say it's going to be meth. In case of a C2, it's going to be eth. In case of a C3, it's going to be prop. In case of a C4, it's going to be bute. In case of a C5, it's going to be pent. In case of a C6, it's going to be hex. In case of a 7, it's going to be hept. In case of 8, it's going to be oct. In case of a 9, it's going to be non. And in case of a 10, it's going to be dec. Okay, that's how we can use these type of word roots. Entire part is already being discussed in the nomenclature. You can refer to that particular part, and I may suggest you to actually practice certain questions which are already present in the NCERT itself to give you a boost. Like if you already know all the things, you can practice all the questions of nomenclature which are already present in the NCERT, and the chapter name is hydrocarbon basically. So you can practice those questions by yourself and the entire part will be cleared. If you find any difficulty related to the nomenclature part, just let me know. Okay, then we will discuss some questions related to that particular part. Okay, now the first thing is clear, that how to write down or how to deal with the nomenclature of that particular hydrocarbon. So let's take 2-3 examples of each part so that we can freshen up the entire concept. Let's start with the first part. So I am directly going to write down the structures which are relevant in the bond line notation. Okay, try to write down the names of these compounds. First of all, if I talk about the numbering, I can start with here 1, 2, 3, 4, 5, 6 and 7. A very simple analysis. So on third position you have a methyl, and total 7, it's going to be heptane, because no double bond, it's going to be heptane. Okay, so this is the first nomenclature. If I talk about the second part, I can say that we have a 1, 2, 3, 4, 5 and 6. So it's supposed to be on second position you have methyl, third position methyl, fifth position methyl. So 2, 3, 5 we have trimethyl, and then we have a 6 chain, so it's going to be hex, single bond, hexane. Okay, so it's supposed to be 2, 3, 5 trimethyl hexane. Okay, I can suggest you to practice certain questions which are already present in NCERT. Okay, you can refer to that particular part. In this case, I'm going to start with here because double bond is nearest. 1, 2, 3, 4, 5. So 5 means I'm going to use a pent. Now double bonds are present twice, then I'm going to add A. So penta, 1, 3 diene. It's going to be penta 1, 3 diene. This is a cyclic structure. So you can say we have cyclo. So I can say that we have 1, 2, 3, 4, 5 and 6. You also have to include, every time you have to include the entire double bond. You cannot say that 1, 2, 3. It's not correct. You have to include the double bond. So basically we have a cyclohexane type of structure. So we have cyclohexa 1 and 4, 1 comma 4 diene. We have double bond twice, so hexa, it becomes hexa. So cyclohexa 1,4-diene, that will be the name of this compound. Okay. Next part, if I talk about the next analysis, this chain will be the parent chain because double bond is included here. So I can say 1 and 2. So on first position, you can say we have cyclohexyl. So 1 cyclohexyl, and then we have ethene. If you don't know anything about the nomenclature, I am again suggesting you to watch all the lectures of nomenclature so that you will be able to catch up whatever thing is happening. We have already discussed elaborately in 3 lectures about the entire nomenclature part. Okay. Last part, definitely I can say we have 1, 2, 3, 4. So that will be the main chain because it includes double bond. So on first position, you can say we have cyclopropyl, and we have a 4 chain, means we have bute, and on second position you have ene, bute 2-ene. That will be the name of this organic compound. I hope this part is clear. I hope this entire part is clear. Just have a look at it. I hope this part is clear. Okay, now let's talk about the next part. After covering the entire portion of nomenclature, the next and basic property related to that particular part is nothing but isomerism. So in case of isomerism, the first part will be the structural isomerism. This part is already been discussed in the portion of isomerism. I have explained the entire part of structural as well as stereoisomerism in the previous lecture. I am just revising the entire part for you guys so that you can correlate whatever thing is happening in case of hydrocarbons. If you haven't watched those lectures, I am again suggesting you to watch the entire playlist related to the structural as well as stereoisomerism part. We have discussed about the simple structural isomerism, geometrical isomerism as well as optical isomerism elaborately in all the lectures. Okay. So in case of structural isomerism, you can see 2-3 phenomena are there which are related to the entire part. First one will be the chain isomerism. Next one will be the position isomerism. These two parts are pretty much relevant in case of simple hydrocarbons. Also you can find if the functional group is present, you can say we have one more part which is related to functional isomerism. But generally in simple hydrocarbons, we do not have these type of isomerism because it depends upon the presence of functional group. So definitely we are not going to focus on that particular part. In this first case, you can see if I talk about the chain isomerism, we can see we are talking about the different chain length of different parent chain length. Means if we have two compounds, isomerism is basically we have same molecular formula but we have different structural formula. That part corresponds to isomerism. So in this particular case, we have the same molecular formula, but if we look at the structure, both the structures are going to have different chain length in the carbon atoms. That corresponds to chain isomerism. Second part is, in this case, you can say chain length is going to be same, but the position of double or triple bond, or you can say side substituent position of side substituent or position of double bond or triple bond, it's going to differ. It's going to differ. Those part corresponds to your position isomerism. Okay, so this part we have already discussed in the previous lectures, so you can watch the entire playlist related to the isomerism part. But one thing which we haven't discussed till now is a very interesting phenomena which only takes place in a single carbon bond structures. It means I am talking about the isomerism, which is going to be actually formed only in case of, only in case of simple hydrocarbons which are alkanes, So if I talk about the isomerism in alkanes, there is one part very specific part, which is known as conformational isomerism, This part we haven't discussed till now, and I told you that in case of hydrocarbons we are going to deal with the conformational isomerism. Now is the time that we are going to discuss about the conformational isomerism. So what happens in this particular case? First of all, the condition for this conformational isomerism is free rotation along carbon single bond carbon. The first condition which is required in this particular case is free rotation along carbon single bond carbon. What happens in these type of isomers? First of all, these are stereoisomers. These are actually stereoisomers. In that case, you can say that a structure, or you can say that molecular formula is absolutely same. Their structural formula is absolutely same, but the main difference here is orientation of atoms or groups along carbon single bond carbon. This is going to be different. That's why we have a specific classification which is known as conformational isomerism. So in this case, the first condition is a free rotation along carbon single bond carbon. What happens? Let's say I'm talking about a structure which is a CH3 and CH3, like this type of structure. So if I want to explain the bonding here, I can say that we have carbon here which is going to form an overlapping with other carbon. So this entire part is going to be a sigma bond, and let's say I have three other atoms which are attached. Okay, so this bond has the condition of free rotation. It's like you have a fixed wall and you are rotating a screw. So you can tighten the screw, you can loose the screw by moving in different direction. So if I'm fixing one carbon, you can rotate next part along the same axis. That is the free rotation. So this condition should be there if you want to talk about the conformational isomerism. I hope this part is clear. I hope this entire part is clear. Okay, now if the free rotation is there, what I can say, again I am talking about the same analysis. Let's say we have this type of overlapping. And let's say now I have H here as well as H here. Let's say I have H here as well as H here. And I am denoting these H as 1, 2 and 3. And I am rotating this entire part. This carbon is, let's say, fixed, and I am rotating this carbon. I'm actually rotating this carbon. So eventually what happens if you are rotating the entire part? First part is fixed, second part is rotating. What happens? You can see there might be a chance that it's going to look like this. It's going to look like this. So we have H, H and H. Now after rotation, there might be a chance that H3 goes to this side, H1 goes to this side and H2 goes to this side after rotation. Again, if you rotate this entire part, there might be a chance that it will create something like that. It will create something like that. That you have now H2, H3 and H1. And this H is a fixed. So every time you can see, if I am rotating the entire bond with respect to these positions, the position of this entire part is going to change. You have 1, 2, 3, then you have a 3, 1, 2, you have a 2, 3 and 1. Again you can rotate, it will become 1, 2 and 3. It will become just like the previous one after rotation. After rotation. So these type of rotations are going to create different type of conformations. After rotation, it's going to create a different type of conformations and they are going to create a molecule which is having a slightly different rotation. So these type of conformational analysis, they comes under the category of conformational isomerism. So the primary condition is a rotating bond. The free rotation is allowed. That is only possible in case of carbon, single bond carbon. I hope this entire part is clear. Now I told you that there are 4 type of projections in the organic compound. First one is wedge dash projection, next one is the Fisher projection, next one is the Newman projection and last one is the sawhorse projection. Now it's time to discuss about the Newman projection because that will be very helpful when you are dealing with the rotation part. Okay, so let's start with the Newman projection. Let's start with the Newman projection. Let's start with the Newman projection. Okay. So let's say I have the structure like this: C, single bond C, then I have H, H as well as H, and H, H as well as H. Okay. Now I am viewing this molecule from this side. I am viewing this molecule from this side. What happens? I can see this front carbon as well as this back carbon. So they are basically arranged like this. We have this single bond is there, one carbon is there, one carbon is there. So if I am seeing this entire part like this, so I can see front carbon and I can see the back carbon. But I cannot visualize the back carbon because this single bond is actually in front of me. So I can only see the front carbon, back carbon should be there. So if you want to represent the entire molecule, you can say that we have the front carbon which is pointed like this and this is the back carbon. Okay, the pointed one is the front carbon which you are seeing and you can see a sphere type of thing which is back carbon. Okay, so this is the first representation. If you are looking, like, it's all about the orientation, it's all about the looking a molecule from a particular angle. So I have this type of structure, one carbon and one carbon. So this is the bond between these two carbons. Okay, 3 hydrogens are there, 3 hydrogens are there. Now if I am looking the molecule like this, I can see only the front carbon and something is there, but I cannot see the bond. I cannot see the bond between these two carbons. So that's why I am making it as like front carbon, dotted one, and back carbon, the round one. Okay. Now this front carbon is connected with 1 hydrogen, 2 hydrogen and 3 hydrogen. So I can see something like that, at 1 hydrogen, 2 hydrogen and 3 hydrogen. In the same way, if I talk about the back carbon, it is connected with 1 hydrogen, 2 hydrogen and 3 hydrogen, just like that. I can say that it must be attached to these 3 bonds. So they must be hydrogen, 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 hydrogen. Now this type of projection is actually known as Newman projection. Newman projection. I hope this part is clear. I hope this part is clear. Let's say I am fixing 1 carbon. I am fixing 1 carbon and I am rotating The next part, let's say the carbon which I am seeing, I am fixing that particular carbon and I am rotating the bond. So I can see different type of conformers which are going to form. So that is the first part, which is the Newman projection. Can we practice some more questions? Yeah, definitely. So let's say I have CH3, CH2, CH3. Can you convert this entire part into Newman projection? You need only 2 carbon atoms for this type of projection. Let's say I am considering this as the one carbon, this is the second carbon. So front carbon will be this, back carbon will be this. So if I talk about the representation, I can say this is the front carbon and this is the back carbon. Okay. Now can you see in this particular case that front carbon is connected with 3 hydrogens only. So I can say we have 3 hydrogens here. Hydrogen number 1, hydrogen number 2, hydrogen number 3. I hope this part is clear. If I talk about the back carbon, again I can see 3 atoms, but 2 atoms are hydrogen and 1 atom is a CH3. So it's supposed to be like a CH3, H as well as H. That is the Newman projection, one of the Newman projection related to this entire part. Okay, we are going to see like what happens when we are rotating the molecule little bit. That part we are going to cover, but this is the Newman projection. So you can say that is nothing but the Newman projection. Okay, let's talk about another example. Let's say we have a CH3, CH2, CH2, CH3. And I am considering this is the one carbon, this is the second carbon. So first of all, we have the front carbon and we have the back carbon. Now this front carbon is connected with 2 hydrogen and 1 CH3. So I can say that we have 1 CH3 and 2 hydrogens and in the back case I can say again this back carbon is connected with 2 hydrogens and 1 CH3. So you can say that must be CH3, this is H, this is H. I can also change this configuration if I am considering this 1 carbon and this is the 2 carbon. If I am considering this as a 1 carbon and this as a 2 carbon. So I can say that it's going to form this type of Newman projection, Now this front carbon is having only 3 hydrogens. So I can say front carbon is having 3 hydrogens. Done. Back carbon in this case you can see 2 hydrogens and 1 ethyl group. So you can say it's going to be C2H5 and then 2 hydrogens. I hope this entire part is clear. Okay, now it's time to discuss about a very specific thing which is known as conformational analysis. Okay, and I'm starting with the first molecule which is ethene. We are starting with the first molecule which is ethane because we need free rotation. So I'm going to include that particular part. Ethane means we have CH3 and CH3. So first of all, what I'm going to do, I can say this is the front carbon, this is the back carbon. First part is H, 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 H. Okay, just have a look at it. Now you can see that this, if I am looking at this front carbon, one hydrogen is like this, second hydrogen will be like this. So if you see like this, you can see that one hydrogen is looking like this and second like this, just in front of each other, like that. This is the first type. Every hydrogen is in front of each other. So you can say there might be a chance that electron pairs on each part, they are going to connect with the electron pair. They are going to interact with each other. So in this case, you can see that the interaction between CH bonded electrons is a maximum here, is actually maximum here. The interaction between these two CH electron pair, one CH electron pair is this, one CH electron pair is this. So you can see these two are in front of each other. So definitely there is maximum interaction between these two parts. Eventually what happens? Fix one carbon, fix the front carbon and try to rotate the next carbon. And generally the rotation is always 60 degree. The rotation is always 60 degree. Try to rotate it. So if you see the front carbon, it's like this. So we have H, H and H. Now if I talk about the back carbon, I can see that H is going here, H is going here, H is going here. It's like the rotation. I am rotating the next part at 60 degree. Now this 60 degree is a dihedral angle. Dihedral angle. It's slightly different if you know the structure of H2O2. If you remember from your hydrogen chapter, the structure of H2O2, it's like an open book structure. It's like an open book structure. Two oxygen atoms, if you open a particular book, that in between the junction, you have two oxygen atom. One hydrogen is on this side, one hydrogen is on this side. So if I'm looking at the book, there is an angle. There is an angle in that particular book. That angle is not directly between the atoms. So that angle will be one hydrogen connected this oxygen and then next oxygen connected with that hydrogen. That angle is actually known as dihedral angle, which is the angle between two planes. Angle between two planes. So that's why this 60 degree I am rotating. That is the angle between two planes. That is the dihedral angle. So in this case, theta will be 60 degree. Now you can see that one CH is present here, but the next CH goes to that side. It is not in front of this particular CH bond. It is like this. So it's slightly rotated, like you can see, like this. You can see slightly rotated. Now you can see in this particular case, the electron pair interaction here is less. So you can see that electron or bonded electron pair interaction is minimum here, Let's say I am giving the name as H1, this front back hydrogen, H2 and H3. Now it becomes H1, H2 and H3. Can I rotate it again? Yeah, definitely I can rotate it again. So now again theta 60 degree. But eventually you have rotated the entire part 120 degree. 60 one time, 60 next time. So total angle will be 120 degree. So you can say it becomes like this. It again becomes like this. Front carbon and hydrogen bond is fixed. Now you can see it again looks like this. That we have H, H and H. But the position now is we have H1 here, H2 here and H3 here. Can I rotate it again? Yes, definitely. Theta again 60 degree. So angle of rotation is 60, but total angle is 60, 60, 60, 180 degree rotation. So you can see this is supposed to be like this: H, 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 H and H. Okay. Now if you see, we have H1 here, H2 here, H3 here. Can you again rotate by 60 degree? Then it becomes again like this, H, 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 H and H. Now this one part will be here, 2 and 3. Can I rotate it again? Yes, definitely. Theta again is 60 degree. So total angle is 60, 60, 60, 60 and 60. That is supposed to be 300 degree. So you can say that we have the structure like this. Again we have the structure like this. So this is H, 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 H and H. This is 1, 2 and 3. And after again theta is equal to 60 degree. I'm going to reach to initial position. I'm going to reach to the initial position. Okay. So you can see this is the bond rotation, free rotation along carbon-carbon sigma bond. Okay. Now there are few important points which you need to understand. First of all, like draw this diagram. Okay. So first of all, if you see that their electron pairs are directly interacting with each other, it means in this particular scenario, you can say that repulsion is going to be maximum because they are in front of each other. The electron pairs are in front of each other. In this case, you can see as they are far apart, the repulsion is going to be minimum. In next case, again they are in front of each other, repulsion is again maximum. In this case they are far apart, you can say again repulsion is minimum. In this case again they are in front of each other, so repulsion will be maximum here. In this case again you can say repulsion will be minimum. Okay, I hope this part is clear. Now what is the name of these forms? When the atoms are actually in front of each other, this form is known as eclipsed form. This form is known as eclipsed form. And this form, when they are far apart from each other, this form is known as staggered form. This form is known as staggered form. So in the case of ethane, we have only two forms. First one is eclipsed and next one is staggered. When I am completely rotating the molecule from 0 to 60 degree, if the rotation, note that one point, very important point, note down, when the rotation is actually, the theta is in between 0 to 60 degree. When it is in between 0 to 60 degree, more than 0 and less than 60 degree, that type of form, whatever is going to form, is known as skew form. Okay, that form when the rotation is more than 0 degree but less than 60 degree, because at 60 degree either you are going to create eclipse form or a staggered form. So in between is the skew form in case of ethane only. I hope this entire part is clear. So if the repulsion is maximum, its energy will be high. So you can say energy will be high. In this case, repulsion is minimum. So you can say if the repulsion is minimum, then energy will be low. So can I draw a diagram in that particular case? Yes, definitely I can draw. So let's say on this axis, I have energy, and on this axis I have angle of rotation. So I am going to start with 0 degree, then we have a 60 degree, then we have a 120 degree, then we have a 180 degree, then we have 240 degree, then we have 300 degree, then we have 360 degree. Yes. So that is the basic analysis. Let's say this is the energy. Let's say this is the axis for maximum energy. And let's say this is the axis for maximum energy, and let's say this will be the axis for minimum energy. let's say this is like this. Okay, so you can say this is supposed to be E maximum and this is supposed to be E minimum. Okay, now at 0 degree they are in front of each other, so energy will be maximum in the starting portion. At 60 degree they are far apart. At 120 degree they are again in front of each other. At 180 degree they are again far apart. At 240 degree again they are in front of each other. You can say at 300 again they are far apart, and 360 again they are in front of each other. So if I want to draw the diagram, I can say this is supposed to look like this. This is supposed to look like this. This form will be staggered form. This is the staggered form, and again this is the staggered form, because they are far apart from each other. So the repulsion between the bonded electron pairs is actually very minimum. In this case they are eclipsed. They are in the eclipsed form. They are in the eclipsed form. They are in the eclipsed form. They are in the eclipsed form when the repulsion is maximum. Now in between that particular part we have skew form. We have skew form. I hope this entire part is clear. I hope this entire part is clear. Now you can say that in every staggered form energy is minimum, repulsion between bonded electrons is again minimum. Okay, in case of eclipsed form you can say that energy is maximum and also the repulsion is maximum. What is the name of this repulsion, whatever we are talking about? So always remember that the repulsion between bonded electrons of whatever form we are talking about, either eclipsed, I can say eclipsed or staggered form. This part is known as torsional strain. This part is known as torsional strain. I hope this entire part is clear to everyone. This is the conformational analysis of ethane. This is the conformational analysis of ethane. So that's how you can create different type of structures. You can again see this is the entire analysis related to the rotation of a carbon-carbon single bond, and you can see different orientations are going to occur in this particular scenario. Okay, so that's the basic idea about the conformational analysis. Okay, in the same way you can actually draw different type of structures. In case of butane also you can draw this type of structure, but that part we are going to discuss in the next session, because we have discussed so many things in this particular session. This is the introduction session, so let's try to focus on one thing, that we are discussing about the conformational type of isomerism, which creates just because of the carbon-carbon's free rotation, and it's going to create a different type of orientation of side atoms with respect to front and back carbon. Okay, I hope this entire part is clear. I hope this entire graph is also clear to everyone. In the case of a butane structure, we are going to discuss about some other forms. First one is going to be the Gauch form, and next one is going to be anti-form, and we are going to discuss how we are going to derive the entire energy curve for different type of forms. Okay, and there are some more repulsions also. Van der Waals repulsion or van der Waals strain is also there, which is going to be created just because of the side bulky atoms. That part also we are going to discuss in the next session. Okay, So I can say that we have discussed about the basic nomenclature, we discussed about the basic isomerism part, as well as we discussed about the analysis of conformational isomers with the help of Newman projection. So Newman projection is also clear. In next class we are going to cover up the entire part of this conformational analysis for butane as well as the cyclohexane structure, because they are very relevant. And in last part we are going to discuss about the preparation methods related to alkanes, alkenes and alkynes. Okay, so that's all from my side. Thank you so much.